Hello. Before you watch this video, it's very important to take some time to read the given carefully and to try to solve the problem yourself. So please do that before you watch the video if you haven't done so already. So what's happening here is that let me read the problem. A small coin is placed on the horizontal surface of the rotating disc. If the disk starts from rest and is given a constant angular acceleration, theta double dot is equal to alpha, determine an expression for the number of revolutions n through which the disk turns before the coin slips. The coefficient of static friction between the coin and the disk is mu s. Okay. Let us kind of set this problem up using our 4 steps first. We have to be careful. We're gonna draw our cylindrical polar coordinate system. EZ is always gonna be along the axis of rotation, so that when the table rotates, the EZ stays fixed. And if I take my origin here, I can draw the position vector from the origin to the particle. The position vector is already in the EX, EY horizontal plane, the plane that's perpendicular to EZ. So I can draw ER, and I'll draw E theta like this. So then maybe EX and EY in the plane are like this. Theta is increasing counterclockwise. I will erase EX and EY just to make the figure neater. Okay, so we're gonna start with the 4 steps, but before we do, let us note that we're looking at the particle when it's still sticking to the surface. So determine an expression for the number of revolutions n through which the disk turns before the coin slips. So before the coin slips, the coin is stuck to the table. So it's R is gonna be constant. Sorry, not the vector, the scalar. And theta dot of the coin is gonna be the same as theta dot of the disk. Same for theta double dot. Okay, so let me write now my position, velocity, and acceleration vectors. R is R ER, V is R dot ER plus R theta dot E theta, and A is R double dot minus R theta dot squared ER plus R theta double dot plus 2 R dot theta dot E theta. And with the simplifications, for R dot being 0, this term goes away, this term goes away, and this term goes away. And we can replace this theta double dot by alpha to get R is R ER, V is R theta dot E theta, and A is minus R theta dot squared ER plus R theta double dot E theta, or theta alpha E theta. Okay, if I want to draw the free body diagram of the puck, I'll just do it here. The forces acting on the coin are the weight, the normal force, and the friction force. So this is a particle on the surface. The normal force is going to have one direction. Here it's going to be along EC. And the friction force has components both along ER and E theta, both vectors that are tangent to the plane where the coin is kind of free to move on. Weight is minus mg EZ. N is NEN, NEZ. And the friction force is F F R E R plus F F theta E theta. Step 3, we'll write the balance of linear momentum. Minus mg Ez plus n En Ez. Excuse me. Okay, that's equal to m, and that's the acceleration, minus r theta dot squared er plus r alpha e theta. So now I can project to get that FFR, the R component of the friction force, the ER component of the friction force is minus m r theta dot squared. The E theta component of the friction force is m r alpha, and the normal force is just mg. Okay, now let's remember what the problem was initially asking for. They're asking for the number of turns before the coin slips. Okay, so just before the coin slips, how many turns would the table have turned? So now before the coin slips, the friction force is static, and the static friction force criterion is satisfied. So what's happening is that initially the disk is at rest and the friction force is 0. And when the disk starts rotating, the friction force starts to increase. The maximum friction force the maximum static friction force just before slip happens is when the magnitude of the friction force is equal to mu Sn. So the friction force is increasing as the disk gains the speed. Just before the coin slips, we have that the friction force magnitude is equal to mu s times the magnitude of the normal force. So if I want to replace the magnitude of the friction force, is gonna be mr, the square root of theta dot to the power 4 plus alpha squared, equal to mu s times mg. Mass and mass cancel out, and I'm left with, if I square both sides, theta dot 4 plus alpha squared is gonna be mu s g over r, all of that squared. Okay, so now I have a relationship between theta dot, alpha, and so on. Now we have to remember that we want to find the number of turns before the coin slips. So far, we found theta dot before the coin slips. It satisfies theta dot to the power 4 is mu s g over r squared minus alpha squared. Okay, and then we also know that theta double dot is equal to alpha. We want to find the number of turns. So in reality, the number of turns is just proportional to the change in angle. The number of turns is proportional to the change in angle. So we want to relate the change in angle with the angular velocity and the angular acceleration. This might remind you of something we have before, of an equation that relates acceleration, position, and velocity without time, kind of related to a dx is equal to v dv in rectilinear motion. Well, there is a similar relationship for theta double dot. So if I look at theta double dot, it's equal to d theta dot by dt, which is d theta dot by d theta, if we write theta dot in terms of theta, and d theta by dt, which is theta dot. So theta double dot becomes theta dot d theta dot by dt. Hence theta double dot, d theta dot by d theta. Hence theta double dot becomes theta double dot d theta is equal to theta dot d theta dot. Analogous to the a dx is equal to v dv. And for practice, you can also show that r double dot dr is equal to r dot dr dot. So if I use this equation, theta double dot d theta is equal to theta dot d theta dot. If I replace theta double dot by alpha, d theta is equal to theta dot d theta dot. Now if I integrate, alpha as a constant, it's outside the integral, d theta from 0 to the theta that I want to find before at slip, just before slip, and then theta dot d theta dot, we're going to integrate it from 0 because theta dot is initially 0 because the disk starts from rest, and then to the instant where we have slip. We will get alpha theta is equal to 1 over 2 theta dot squared, and this is valid before slipping happens. So it is valid in this instant, just before slipping valid, is just before slip happens. So if I kind of match the two equations and plug them in, I'll get that theta dot to the power 2 is 2 alpha theta, which is equal to the square root of mu s g over r squared minus alpha squared, and theta is 1 over 2 the square root of mu s g over r squared times alpha minus 1. So this here is the angle at which the coin starts to slip. Now if I want to find the number of turns before the coin starts to slip, all I have to do is divide theta by 2 pi. So for every 2 pi, the disk would have made 1 turn. So if I divide theta by 2 pi, I'll find the number of turns that the disk rotates before the coin starts to slip, just before the coin starts to slip.